In our last two lessons, we introduced the Fourier series and derived the analysis equations for finding coefficients. Today, we explore key properties that make working with Fourier series much more powerful. Let's start with an important bookkeeping detail. Different textbooks use different scaling conventions. If we write the synthesis as C1 times the sum of xk e to the jk omega 0 t, and the analysis as C2 times the integral of x of t e to the minus jk omega 0 t, the only requirement is that C1 times C2 equals 1 over t. In Oppenheim's convention, C1 equals 1 and C2 equals 1 over t. In Haken's convention, the factors are swapped. Both are correct. Here's one of the most powerful Fourier series properties, differentiation. If x of t is a periodic signal with Fourier coefficients x sub k, then the derivative y of t equals dx over dt has coefficients y sub k equals jk omega 0 times x sub k. Each coefficient gets multiplied by j times k times the fundamental frequency. The j introduces a 90-degree phase shift, and the factor k means higher harmonics are amplified more. For the nth derivative, we raise the factor to the nth power. Y sub k equals jk omega 0 to the n times x sub k. More importantly, this property works in reverse. If we know the coefficients of a derivative, we can find the original signal's coefficients by dividing by jk omega 0. Let's find the Fourier coefficients of a fundamental signal, the periodic impulse train. Delta t of t is the sum of delta functions spaced t seconds apart from minus infinity to plus infinity. Using the analysis equation, x sub k equals 1 over t times the integral over one period of delta of t times e to the minus jk omega 0 t dt. The shifting property extracts the exponential at t equals 0, giving e to the 0, which is just 1. Therefore, x sub k equals 1 over t for all k. Every single coefficient has the same value. This gives us a beautiful identity. The periodic impulse train equals 1 over t times the sum of e to the jk omega 0 t. Let's visualize this remarkable result. Plotting the magnitude of x sub k versus k, we get a perfectly flat spectrum. Every harmonic from minus infinity to plus infinity has the exact same amplitude, 1 over t. This is why the impulse train is so fundamental in signal processing. It contains all frequencies with equal strength. No other periodic signal has this flat spectrum property. Now let's put the differentiation property to practical use with what we call the derivative trick. When a signal has sharp transitions or discontinuities, computing Fourier coefficients directly can be very painful. Instead, we differentiate the signal. Discontinuities become impulses, and impulses have simple, known Fourier coefficients. We then recover the original coefficients by dividing. X sub k equals y sub k divided by jk omega 0. This technique converts a difficult integration problem into simple algebra. Let's demonstrate on a square wave. Consider a square wave f of t with amplitude plus m for 0 less than t less than pi and minus m for negative pi less than t less than 0, with period t equals 2 pi. Computing f sub k directly requires careful integration. Instead, let's differentiate. The derivative g of t equals f prime of t produces impulse pairs at each discontinuity. Positive 2m times delta at t equals 0 and negative 2m times delta at t equals plus or minus pi. Using our impulse result, g sub k equals m over pi times the quantity 1 minus cosine of k pi. Since cosine of k pi equals negative 1 to the k, for odd k this gives 2m over pi, and for even k it gives 0. Dividing by jk to get f sub k, we obtain f sub k equals negative j times 2m over k pi for odd k and 0 for even k. To develop intuition, let's visualize Fourier synthesis as rotating phasors. The fundamental harmonic k equals 1 traces a large circle in the complex plane with radius 4m over pi. The third harmonic k equals 3 traces a smaller circle, 1/3 the radius, but rotating 3 times faster. The fifth harmonic is smaller still, 1/5 the radius, 5 times the speed. As these phasors rotate, add their tips together. The sum traces out the time domain signal. With just 3 harmonics, you can already see the square wave taking shape. Let's watch the convergence step by step. Starting with just the fundamental, f1 of t equals 4m over pi times sine t. It's a smooth sinusoid, the crudest possible approximation. Adding the third harmonic gives f2 of t with sine 3t over 3 included. The waveform develops a hint of a flat top. With the fifth harmonic, f3 of t shows clearer corners and flatter plateaus. By 7 harmonics, the shape is unmistakably a square wave. But look carefully at the transitions. There are sharp oscillations that overshoot the target amplitude. These ripples don't disappear no matter how many terms we add. This persistent overshoot is the famous Gibbs phenomenon. At every discontinuity, the truncated Fourier series overshoots by approximately 9% of the total jump. For our square wave with jump size 2m, the overshoot is about 0.18 m. As we add more harmonics, the overshoot gets narrower, but its peak value stays at 9%. The oscillations compress into a thinner region around the discontinuity, but the maximum overshoot never vanishes. This is not a failure of the Fourier series itself. The infinite series does converge correctly. It's specifically the truncation to finitely many terms that causes this effect. Let's examine the coefficient spectrum of our square wave. Plotting the magnitude of f sub k versus k, we see a striking pattern. Only odd harmonics have non-zero coefficients, reflecting the half-wave symmetry. The magnitudes follow a 1 over k envelope shown by the dashed curve. This slow 1 over k decay is characteristic of signals with jump discontinuities. Smoother signals would have spectra that decay much faster, like 1 over k squared or even exponentially. Let's review the 5 key results from today. First, scaling conventions. C1 times C2 must equal 1 over t in any Fourier pair. Second, differentiation in time multiplies coefficients by jk omega 0. Third, the periodic impulse train has a flat spectrum. X sub k equals 1 over t for all k. Fourth, the derivative trick turns discontinuities into impulses for easier coefficient computation. And fifth, truncated Fourier series exhibit the Gibbs phenomenon, a persistent 9% overshoot at discontinuities. These tools are essential for analyzing any periodic signal in engineering.